Hello everyone, today we'll study about air refrigeration system of type 2, that is simple air evaporative cooling system. Here, as discussed earlier, it is the same apparatus. The only difference here is it has an extra evaporator. This extra evaporator walks us a step forward and helps us to reach slightly better cooling. That is, the evaporator contains an evaporant. This being an open cycle, the evaporant accepts heat energy from this passing gas, that is air. We have air into the system. So the evaporant present inside the evaporator accepts the heat of the gas and it evaporates. As it evaporates, it exits from this outlet, and this being an open cycle, the vapor form of the evaporant is diffused into the ambient. So over time, as the process takes place, the level of the evaporant decreases. So before the flight takes off, it is mandated to carry significant calculated number of evaporant that should last the process from takeoff till the landing. Else we could use a closed system wherein, for example, if the evaporant would be water, then water accepts the heat from the air, it converts to vapor. Again, we can put some condenser here which condenses the vapor back to water, and the water is sent back to the evaporator. But this is an open case, so the evaporant definitely diffuses into the atmosphere and decreases over time. So we need substantial amount of evaporator to make the process of refrigeration continue throughout the flight timings. Now, there are majorly three types of evaporants used: hydrogen, alcohols and ammonia. So talking about each and every process, as the ambient air enters the conduits, it undergoes ramming effect from 1 to 2 dash. From 2 to 3 dash, it goes into the main compressor. It was supposed to go straight, but due to irreversibilities during the compression, it goes a curve adiabatic process. It reaches 3 dash. Now this air goes into two ways. One way, it goes into the combustion chamber, it increases its kinetic energy, it goes to the turbine helps rotate this shaft, and this shaft powers the main compressor. Talking about this path, the air goes into the heat exchanger, wherein this air is cooled using the ram air. The cold ram air cools the compressed air. So we go from 3 dash to 4. The ram from 3 dash we go to 4, somewhere here. Now from 4 to 4 dash, this air is cooled more. So from 4 it passes through the evaporator. In the evaporator, the evaporant present inside the evaporator accepts the heat from the tube, the tube present in the air present in the tube, and it accepts its energy. It evaporates and lets the air cool down. So from 4 to 4 dash, the air cools down more. Now from 4 dash to 5, the air in the system expands and cools down. We can also see that the ram air from the heat exchanger goes into the cooling fan area. So cooling air fan is just the fan which rotates this shaft, which in order helps to rotate this turbine. So this air rotates the fan. This air is exiting to the atmosphere. This is the cooling air fan. This is the cooling air. This air cools the system, so hence it is known as the cooling air fan. It rotates this fan, it rotates the shaft, and this shaft is connected to the cooling air turbine. So this air is locked back into the cabin using a cooling air turbine. It is expanded and sent back to the cabin. It is expanded to the cabin pressure. There are some considerations to be made, that the air outing from the system has to be expanded to the cabin pressure, and also the temperature of the air that is made to outlet from the refrigeration system should not be so cold compared to the cabin air. So for example, on an average, the cabin temperature of any aircraft is somewhere around 22 degrees Celsius, and if the air coming out from the refrigeration system is somewhere around 15 degrees Celsius, then it is very bad, because it can cause condensation, it can choke the system, and it can also cause over chilling of the aircraft. So we from 4 dash to 5 it reaches here, and after 5 dash there is an external apparatus which helps us to regulate the temperature which is near to the cabin temperature. Therefore we increased the temperature slightly. Rather this point was better if talking about the refrigeration. If talking about the coldness point of view, then this temperature is lesser than T6, but we went an extra mile to slightly heat it up to the cabin to match the cabin temperature, to make sure that there is not much temperature difference between the refrigerated air passed to the cabin and the apparent temperature of the cabin. So now talking about the calculations. MA represents the mass of air required into the system. So M simply means MA into MA equals 210 into Q by Cp into T6 minus T5 dash. This is the refrigeration zone. The refrigeration, like we had in VCRS, the refrigeration used to occur between 0.4 and 0.1. Similarly, in this system, the refrigeration occurs between 0.5 dash and 6. So here we can see this is the equation when Q is in ton of refrigeration. The power or the work input equals m dot by 60. 60 was done because the m dot was per minute. To convert it to per second, it was divided by 60. Now this remains same, T3 minus T3 dash minus T2 dash. These 2 points, the compressor work points. This is in kilowatts. Therefore COP equals QL in kilowatts divided by W net in kilowatts. I would always suggest to convert all terms in kilogram per second and kilojoule per second to have a better calculation efficiency. And now, as we talked earlier, before the flight takes off, the amount of evaporant to be present into the evaporator tank should be calculated as it decreases over time. As it is an open cycle, it doesn't regenerate, it doesn't replenish, it is diffused into the air as per operation. So the required amount of evaporant is mass of evaporant is equal to QE. QE is the heat transfer taking place, or the heat transfer to be taken place into the evaporator, into the time. This time is the time of the flight, the time interval between from the takeoff till the landing. How much time the plane flies or how much time the plane needs refrigeration, divided by HFG of the evaporant, that is latent heat of the refrigerant. Latent heat represents the heat required for the evaporator to evaporate. So this is the equation. Mass of the evaporant in kg equals QE, the amount of heat transfer that should be taken place into the evaporator into the time of the flight divided by latent heat of the evaporant. So I hope you got it. This was simple air evaporator cooling system. Thank you.